so I'll record this. Okay, so we've oftentimes taken functions like this, and when we wanted to find the area under them, don't miss this. Already lost some of you. That was fast. If we wanted to find an area like this one, we would sort of think of it in rectangular, like a rectangular sort of fashion. So we'd break it down into rectangles like this, right? And this is a convenient way to do things because areas of rectangles are very easy to find, and you can always get the y coordinates, which represent like the heights of these rectangles. All you have to know is the function, okay? So you basically use the function as your heights, and you use like a dx for your widths. So this is like dx, and this is always like f of x, right? And so the areas are f of x dx. This is what we call a differential area. It is the area of an infinitely thin rectangle, okay? This method would not work very well in polar worlds, okay? And here's the reason why. First of all, the functions look a little different. Instead of having one y for every x, they have basically one r for every theta. Or that's sort of the basic idea anyway. There are exceptions to it. But imagine a graph like this one. This is sort of a good one to study. This is what we call a cardioid, okay? If you try to break this thing into rectangles, you're going to have two problems. One, the rectangle's heights are dependent, or I should say the rectangle's, since this isn't a function, you have a rectangular portion above the axis and one below the axis. So that's kind of one problem with this situation. The other thing is you don't really have the function y, so you'll never really know how tall the rectangle is, right? Typically when you're given a function like this, you're told that r is equal to 3 plus 3 cosine or something. So how is that going to help you find the heights of the rectangles? You see what I'm saying? So this just isn't the right approach. The concept is okay, the idea of splitting the shape up, but rectangles is not the right way to go. So here's what we basically do. Let me draw this a lot larger. Instead of using rectangles, since everything is either radial or angular, we break the area down into these things. So you might say, well, what is that? Is there a name for that shape? Not really. Probably the closest thing we have in geometry to this is a sector. Do you guys remember sectors? Okay, sectors look like this. They're wedges, parts of a circle, like a slice of pizza. Slice of pizza is a sector. Next time you go to Z Pizza, you can say, can I have a sector, please? Okay? How much for 2 sectors of pizza? So these are sectors, but this isn't really a sector either. Why?
Because it's not a perfect arc. It's an extent radially.
Yeah, this is not technically a circular arc. It's close, maybe, in some cases, but it's not technically circular. So this is a brand new object, but the closest thing we have is a sector. And it is really sector-like if we keep the little theta really small. Okay? So we keep the angle there in this center real small, real thin. So if we keep the slice real thin, specifically like d theta, infinitely thin, then this really is like a sector. Okay? So let's look at a sector up close, because we need the area of a sector now. Okay? So a sector has interesting properties. All of these are r, and this distance right here is r theta, where theta is the angle at the center. It's called the central angle. Okay? So what is the area of this? Well, you can look up the area of a sector in any pre-calc book. It's actually just 1/2 r squared theta. Or you can look at it as a triangle, because the closest thing in, the next closest thing to this shape in geometry is a triangle, right? It looks almost like a triangle. Notice that this distance is r, just like the other 2 r's. So if you treat these things as sectors, and you treat sectors as triangles, you can kind of figure out what the differential area of the polar sector is. So what would be the area of this triangle if we use 1/2 base times height? 1/2 times base times height would give would 1/2 times base times height give us? 1/2 r squared theta, right? Now I said we should probably keep our theta really small. That way, this polar sector is like a circular sector and in turn like a triangle. So if we're going to use this logic, we need to keep it like a d theta, really, really tiny and thin. So let's keep this as d theta. Kind of working backwards here, we can see that the differential area of a polar sector is 1/2 r squared d theta. Okay? Whether you're thinking of it as a triangle or a sector or a polar sector, in the infinitely small approximation, they're all the same shape. If that makes sense. Okay, so that is sort of our integrand, I guess you could say. And if we want to find a full area, we would just slap an integral symbol on both sides. So bam, bam. Okay? So this is why in my notes I said, right here, that the integral of 1/2 r squared d theta will provide us with a polar wedge, like a polar sector. Okay? I'm sorry, the integral will actually give us the whole sector, all the sectors. It combines all the sectors. Okay, so the trickiest part then is trying to come up with some kind of meaningful limits of integration. That's kind of the hardest part, really. So we'll just call them angles alpha and beta. And this picture kind of says it all right here. Okay, and here's the area for it. And maybe you now kind of see that triangular look, and that's where we get the 1/2 and the r squared and the theta, the d theta. Okay, now what is this? This looks like crazy rocket science. It's not. Okay, so what's going on in the second picture is we kind of have two wedges. So we have this blue wedge. Let's do the red. Larger one's red. Large red sector. We're going to pretend this is a sector. And that thing has area 1/2 r squared d theta, and if you integrate it, you get the whole thing. And then there's a smaller one inside it. We'll just treat this as its own sector. Okay? And that one has 1/2 r1 squared d theta for its area. And the blue space is just in between them. So if you took the red pizza slice minus the black pizza slice, you would get this little blue crust here. See? The crust of the pizza. So I kind of just rounded everything off and made it nice and smooth. But in the infinitely small case, these are truly almost round, you know? So basically I'm just saying if this integral minus this integral, you're getting the area inside here and you're subtracting off the area inside here. So it's like two concentric pizzas, one on top of the other. Okay, so then since these have the same limits of integration, you can just combine them into one integral. Notice how similar this looks to Washer method. In Washer method, this is a pi r squared minus r squared. And it's a dx, of course. But in the polar method, it's a 1/2, and then there's an r squared minus r squared d theta. Okay, question?
Because you're treating it kind of like a triangle, is it exact? Curves and everything?
You remember in the limit situation, you're actually shrinking that d theta down to 0. So it's so small. Remember what Euler said, when you zoom in on any curve, and there are exceptions to this, but most curves, especially differentiable ones, all differentiable curves, when you really zoom in on them and look closely, they look straight anyway, right? So we can treat them that way. Probably what I should have drawn is a series of red small wedges like this. So here's a red small wedge, and inside it a black small wedge, and subtracting the red minus the black gives us this sort of a crust type thing. And then the integral collects them all. So when you make them real thin, they really are sectors, or even triangles, really, if you want to think of it that way.
So we can find the area of a pizza crust by doing that?
Yes. Yes, you could do that. Okay. That's kind of how you make friends. I made all three of my friends that way. Okay. So we have formulas now. Hopefully we kind of understand them. And they're really not that hard to memorize. Like I told you, the hardest part is getting that limit of integration figured out. Okay, so for this you kind of need your calculator. Okay? We're not going to actually do the integral on the calculator like it says. We'll do the integral by hand. But I think it's important to have the calculator anyway because we need to be able to see the limits of integration, and the calculator can really help with that. Question? You want to borrow one? Okay. Who else would like to borrow a calculator? All right. And I'll have my emulator up here too. So the first thing I want to do is write down the formula that I'm going to need. So I already know that the area is going to be the integral from something to something, and then it's supposed to be r squared d theta, see, where r is actually a function. So it's 1/2 r squared d theta. So it's really f of r. It's a function. R is a function. Okay, so how am I going to figure out my limits of integration? For that, I'm going to cheat a little and use my calculator. Okay? Now, I technically don't need a calculator that much because I teach these polar graphs to my pre-calc students all the time, so they're kind of fresh on my mind all the time. But maybe you didn't remember that this is a rose. Okay? I would doubt many of you remember that that was a rose. So how did I get that on my screen? I think I showed you this yesterday, but you would put your calculator in polar mode, right? Polar mode. And then you would make sure it's in radians. Anytime there's sines or cosines going on and you're doing calculus, make sure you're in radians mode. And then when you press y equals, you can see that you have this brand new screen, r1 equals. So I just typed this function. Now before you press graph, just know that you almost always need to play around with the domain. So that's under window, and the zoom in, zoom out, that just sort of fixes x min, x max, and so forth. But you need to modify theta min and theta max by hand. So you got to get into this screen and you've got to change these values around. So what I usually like to do is start with like 0 to pi over 2 or something. My objective is to see how much rows I get when I graph 0 to pi over 2. Maybe it's half a rows. Maybe it's a fourth of a rows. Let's see. It looks like it's 1/4 of the whole rows. Okay? That's very important. Now, I wonder if I could have gotten a fourth of the rows by doing like less angle. Maybe I could have done that with pi over 8. So let's try that real quick. So I'm going to go back under window, and I'm going to type pi over 8 here. I did not get a quarter rows from using pi over 8. How about pi over 4? Nope. How about pi over 2? Yes. Okay, so I'm convinced. I was just goofing around a little bit. It seemed like when I did pi over 8, I got an eighth of the rows. When I did pi over 4, I'm sorry, when I did pi over 8, I got a 16th of the rows. When I did pi over 8, I got like an eighth, maybe pi over 4, I got like an eighth of the rows. But when I did pi over 2, I got one loop of the rows, one petal. Okay, so those are my limits of integration. Okay, so coming back to this, I only want one loop. It says in the instructions, find the area within one loop of the rows. So even though the rows has 4 petals, they're asking us just to find the area of one of them. So I've decided that this is going to be 0 and pi over 2. Don't take that for granted, okay? Don't just assume, hey, 2 pi is a full circle, and I'm going to do 1/4 of that. Don't assume that. That's what happened here, but that's not always what happens. Question?
So like, I don't know if this is a good question or not, but you know, like, say it's pi over 2 is only one loop. Does it matter like which loop it's at?
No. We can find the area of any one of those 4 loops. In fact, we don't have to use 0 and pi over 2. We could use pi over 2 and pi. That would give us this second loop in the rows over here at quadrant 2. Okay? Oh, and also don't assume that when a point is in quadrant 2, that its angle is between 90 and 180. That's not true either. Because r can be negative sometimes. So it gets kind of confusing. I think the safest thing to do is to graph on the screen and play around with like I was doing and figure out, okay, 0 and pi over 2 made my one loop. integration. Now, the integral itself is a little hard to do, so I'll do that on a separate page. Yes?
So, would you just do this as like, if you wanted to get all of it, would you do 0 to 2 pi, or would you do 4 times that?
0 to 2 pi might work, or it might just give you a big fat goose egg in the end, if the areas are canceling one another out. So the safest thing to do is, if you want the area of the entire rows, to multiply by 4 if this works out. Does that answer your question? Okay. Another question?
I can't get it on my calculator.
Oh, you're in polar mode and radian mode?
Yes.
Okay. And did you do a zoom standard?
Like when I hit graph, it just says arrow window range.
Oh, that means that you have your x min like bigger than your x max or something. There's actually a typo in your window screen somewhere. Just do a zoom standard, it should fix it. Good question. Okay. So I need a separate piece of paper for this integral. It's kind of a pain. Getting the antiderivative, you know. So this is sine squared 2 theta. So there are two identities that you really need to know, okay? You really need to know that cosine 2 theta is 2 cos squared theta minus 1, and cos 2 theta is also 1 minus 2 sine squared theta. How many of you remember these identities? There was a time when you actually had all this memorized. The reason these two are so important is because in the first one, if we isolate cos squared, we get cos squared equals 1/2 plus 1/2 cos 2 theta. This is your friend, okay? Because anytime you're trying to integrate cos squared, you can quickly change cos squared to this. Which is easier to integrate, cos squared or cos 2 theta? Cos 2 theta is easy to integrate. It's 1/2 sine 2 theta. So that's going to be easier to integrate. So we're going to always change cos squareds to this when we're trying to integrate. The second one, if we use the second one to solve for sine squared, we can get a similar sort of thing for sine squared. So sine squared is 1/2 minus 1/2 cos 2 theta. This will help us replace the sine squared if we ever need to. And on this particular problem, we were trying to solve this integral. Right? It had a sine squared 2 theta. I can't integrate that. Maybe by parts or something, but that's no fun. So let's just change it.
Is there supposed to be a 1/2?
Yes, there's a 1/2 out front. I'll keep it out front. Thank you. What am I going to change the sine squared to? I will always change sine squareds to 1/2 minus 1/2 cos 2 theta. Now in this problem, I already have a 2 theta on the inside, so it's going to be 1/2 minus 1/2 cos 4 theta. Okay, so don't take this too literally. This is just saying, if you're trying to replace the sine squared blah, it's 1/2 minus 1/2 cos 2 blah. Here we have a sine squared 2 theta, so we have 1/2 minus 1/2 cos 4 theta. This is very easy to integrate now. Let's pull out the half first, though. We got it. Now we have a 1/4 here. And we're no longer threatened by this integral. Okay, so we have a 1/4 here, and then we have, for our antiderivative, theta minus 1/4 sine 4 theta. Okay, when you plug in pi over 2, you get pi over 2 here, minus, and then this is just going to be a sine 2 pi, that'll vanish. When you plug in 0, both of these vanish. So there's like 4 things to plug in, but only one of them even counts. So I'll show my work here at the top. So let me bring my work up here. You plug in the pi over 2, and you get pi over 2 minus 1/4 sine 2 pi, but that's gone, minus, and then 0 minus 0. So those are gone. The answer is just pi over 8. So who knew that on a polar rose, the area in here is pi over 8? I'm not surprised to find a pi, but I didn't know it was pi over 8. Okay? Interesting. So I'm just going to transfer my answer over to the other page. Like I said, you could have done that on the calculator screen. You could just type this integral as is.
They dock you because if you, I don't know for sure, but I doubt it's going to give you pi over 8 as the answer. If you just
Your calculator won't say pi over 8, but if you get, a number on your screen and you suspect it's a multiple of pi, try dividing the number on your screen by pi to see what multiple of pi it is. So let's say your calculator displays 0.392 something. Divide that by pi. Ooh, 0.125. That's 1/8 pi. See?
So should you put pi over 8 or would you just round the decimal?
I think we should put pi over 8. This problem most likely would be a calculator active problem on the AP exam, and if it wasn't, it would have you stop actually when you got to here. If you look at the FRQs I gave you, both of them, part A, were polar integrals, and they both said write an integral. They never said solve it, right? So you actually stop here. Okay. Determine the area of the region enclosed by the polar curve 1 minus cos theta. So we can still write down the formula of the day, right? There's a half. We're going to keep it out front. And it's 1 minus cos theta squared d theta. What are the limits of integration? Okay, so let's get our calculator out and let's see what it looks like. New function, 1 minus cos theta. Let's see what it looks like. That's not a whole graph. Remember I have my calculator set for pi over 2? Let's get back into window. Let's see if it will finish the graph if I let it go from 0 to pi. Looks like maybe half of something. Let's try 0 to 2 pi. What I'm doing is not really that optional, okay? There are other ways to figure this domain out, but it's hard to do. You have to really understand periodicity of trig functions. So just play the game with me here. Okay, I just did 0 to pi, and it looked like I had half of something. I then did 0 to 2 pi, and it looked like it sort of closed in on itself. I wonder if there's any more interesting features to this little picture. Maybe I should let it go like all the way to 4 pi, see if I get any additional interesting features. 4 pi. Okay, just graphed. It's still thinking, but no additional features were added. So what just happened? It graphed the same thing twice. Okay, now I'm convinced 0 to 2 pi is the domain of this shape. This is called the cardioid. Okay, now I have to use 2 pi. I can't use 4 pi, or I will literally get twice the area. Okay? So we're just going to stick with 2 pi. We kind of decided that by playing around here. And since they asked us to find the entire area, we're not doing a part of it, we're going to go 0 to 2 pi here. Now if this gives me a big fat goose egg in the end, I'm going to go back and break it up into sections. Maybe I'll do like 0 to pi and then double it or something. Because I know the area that thing wasn't 0. Okay, so this integral is kind of like the other one we just did. You've got to kind of flow it out. And then it's going to have 3 parts, and you're going to integrate them. So let's do that on our separate page. Okay, so we're integrating from 0 to 2 pi. We've got a 1 minus cos theta here. So let's just go ahead and FOIL that on our first step. So this is going to be 1 minus 2 cosine theta plus cosine squared theta d theta. So I already FOILed. I don't like the cos squared theta. Not a fan of that at all. So let's replace that thing. Do you guys remember what we replaced cos squared theta with?
1 plus, or 1/2 cos 2, 1/2.
1/2 plus 1/2 cos 2 theta. Yes. Try to memorize that, okay? So it looks like I have a 3/2 minus 2 cosine theta plus 1/2 cosine 2 theta. So my antiderivative will be 3/2 theta minus 2 sine theta plus 1/4 sine 2 theta. That's supposed to say sine 2 theta inside the bracket, sorry. Bye. Okay, fortunately, I mean, there's like 6 things going on, right? Because you got to plug in the 2 pi into 3 things, and you got to plug the 0 into 3 things. When you plug that 2 pi in to the first term, you actually get something meaningful. But when you plug the 2 pi into this part and this third term, you get 0 both times. And when you plug in the 0, you get 0 all 3 times. So really, you only have to plug the 2 pi into this very first term. So the answer is 1/2 times 3/2 times 2 pi. So what I'm saying is the arithmetic ends very easily. 3 pi over 2. Okay, so these are the kinds of problems where I always wonder, did I do it right? You know what I mean? I got an answer, right? But after playing around with the calculator, trying to get the domains, I could figure out the limits of integration. I just never quite feel right in the end, you know? I don't feel like I should have needed that calculator, first of all. And you can get to the point where you don't need it, but there's a very easy way to check that your answer is reasonable and correct. Okay? So go back to your graphing screen here. Notice that this entire image fits nicely inside of a box. It's really not a very big box. It looks like it's maybe 2 inches, 2 units tall, you know, maybe 2.5 wide. This area inside the cardioid should be roughly 5, less than 5. And 3/2 pi is 4.5, right? Roughly 1.5 times 3.14. So we're dealing with a reasonable answer here. The cardioid basically fills this little box, and we're getting 4.5. So you guys understand what I'm saying? You kind of judge the reasonability of your answer. Now, if you happen to get like 9 or something, that's impossible. It can't even fit inside that box. How could it be 9? Maybe you forgot the half that goes in front on today's formula, right? Or forget this half. So I almost forgot it electricity, right? Okay. So that's just something I always do. Sometimes when it's multiple choice, that's all I do. All I do is draw the little box around the shape, and I'll look at how much of that box is shaded, you know. It's like, oh, it's half shaded, the area is about 7, and I look at my 4 choices, and the only one that makes any sense is C. Yeah, it's cheating, but you're using your brain too, right? Okay, so at least check the reasonability. Let's go to the third example. Write an integral to represent the area inside, or of the region inside the polar curve r equals 3 cos, and outside the curve r equals 2 cos. Ooh. Okay, so there are 2 things going on. There's a 3 cos function and there's a 2 cos function. So let's do 3 cos theta, see what that thing looks like. And let's do 2 cos theta, and let's graph it. Oh, I think what they want us to do is find this area in here. This little crescent moon thing. Okay, well, remember the wedges I drew earlier? This one is kind of like a 2-wedge ordeal. So you're going to take the area of this large black wedge, right, minus the area of this smaller red wedge to get the blue wedge. In other words, we're going to use the second formula up here. Remember, I gave you 2 formulas today, not 1. We're going to use this one up here in green. Make sense? Obviously, you do outer minus inner, otherwise you're going to get a negative area. Okay, any questions so far? All right, so we can at least get the integral set up. We're going to have to be really careful with our limits of integration. Okay. All right, so we're going to set up our integral. This time there's a halfer out front, and there are 2 functions, squared and subtracted. So this one is the 3 cos theta, and this one is the 2 cos theta. Does anyone care to guess what the limits of integration will be? 0 to 2 pi? Are you saying that because it's like a full circle? Okay. How sure are we that it's 0 to 2 pi? Not, right. So it turns out that the correct limits of integration are not 0 to 2 pi. Okay, is there a question? Go ahead.
Yeah, I think you said it was outside minus inside.
Yeah, 3 cos is the bigger circle here. 2 cos is the smaller circle. So if you're not sure about that, you can graph them one at a time to check. Okay. I'm going to do it anyway. I probably should have graphed these one at a time. 3 cos is the bigger one. 2 cos is inside it. Naturally, but still, you want to be sure, right? In fact, ours can be negative sometimes. That's what really messes this up. So I have this set for 0 to 2 pi. Now, does that mean that 0 to 2 pi is the right answer for the limits of integration? No. Watch what happens when I change 0 to 2 pi to 0 to pi. You think I'll get the whole image? Ooh. Okay, almost put 2 pi for my limits of integration. But even 0 to pi gives me this full graph. Just for kicks, let's try 0 to pi over 2. See if that gives us a full graph. No. 0 to pi over 2 did not give me a full graph. 0 to pi gave me the full graph. Okay, so what that means for our problem is that we're going to be using 0 to pi here. Okay? All right, glad we checked. Notice that this is just 9 cos squared minus 4 cos squared. In other words, the inside collapsed to be 5 cos squared. And if you don't mind, I'm going to pull that 5 all the way out of the integral. Okay, we've already integrated this a couple times. But we said that you can replace this with a 1/2 plus 1/2 cos 2 theta. I wrote 2 pi, didn't I? Why did I write 2 pi? Oh, I just said... I just got done making a really strong argument that it wasn't 2 pi, and then I wrote 2 pi. Maybe I'm just hungry and I want to eat 2 pies. Okay, let's pull out that halfer too. So let's pull out that halfer and make this a 4, because I'm running out of space. Okay, so these are just 1s. And the antiderivative is just theta plus 1/2 sine 2 theta, 0 to pi. And fortunately, the same thing happens to happen the last 2 times. When you plug in that pi, you get pi plus 0, and then you plug in the 0, you get 0 for 0. So you're just going to get 5/4 pi for a final answer. 5/4 pi. Okay, I'll write my answer in green right here so you can see it. Answer 5 pi over 4. Let's check that it's reasonable. So 5/4 pi is roughly 4.5 again. Okay? So going back to our graphing screen, if we surround this with a box, like this, this is kind of a 3 by 3 box. In other words, its area is 9. The area that we're interested in, we're saying, is about 4.5. Is that believable? 5/4 pi is 1.25 times pi, which is roughly 4.5. Is it reasonable to say that this crescent fills about half the area of the red box? I think it's reasonable. Usually when they're not reasonable, you'll know. It's like way, way off. Okay? And then the second thing we can do to check is this entire problem needed no calculus at all. In fact, this problem was kind of ridiculous in the first place. Maybe you've seen this problem actually on the SAT, a circle within a circle. Can't we just do pi r squared minus pi r squared here? These truly are circles. The radii of the circles are, the bigger r is, if you look really closely, it's 3/2. And the little guy has radius 1, if you go back and look closely at your graphing screen. In other words, it's 9/4 pi minus pi 5/4 pi. Sorry to make you do the calculus, but do you know where pi r squared comes from?
Calculus.
Exactly. So I don't feel too guilty, because honestly, if you ever do forget pi r squared is the area of a circle, you can rederive it. You really can. So that's the last thing I want to show you guys, is how to derive pi r squared using a polar integral. Okay? So this isn't in the notes, but I think it's healthy after years and years of using pi r squared to see why it's true. You know? Imagine a circle. In polar coordinates, this equation would just be r equals a number. R equals 5, r equals 1, whatever. Okay? If you follow the rule of the day, and you're trying to find the area of this circle, you would integrate, you do 1/2 times integral from 0 to 2 pi of r squared d theta. What is my r function? Simply a. A is truly a constant, so the a squared pulls out, leaving a 1 right here, just a lonely 1. What is the antiderivative of 1? Theta. There it is, pi a squared, the area of a circle. You plug in the 2 pi, and then you do a squared over 2 times 2 pi, pi a squared. The area of a circle has always been pi r squared, and finally on our last new lesson in high school math, we finally see why. So this is the end of Calc BC right here.
Wait,
Okay.
we're not going to learn anything new.
You can learn anything new?
No, I said we're not going to.
We will. I'll teach you some more things after the AP test. High school math. Technically this is college math anyway, but yes.
Wait, can you like write out that how you got pi a squared? I don't know why I'm just not getting
If you plug in the 2 pi
it. Yeah.
for theta, you get 2 pi. If you plug in 0, you don't get anything. So a squared over 2 times 2 pi is just pi squared.
That was multiple. 2 pi times theta.
Okay.
And that's
2 pi theta.
All right. So there you have it.
what happens in
And the book pages have a bunch of integrals too that you can practice. I want to say one little thing about the lemniscates. So when you guys do the lemniscate problem in the textbook, okay, you have to, you're trying to get the area right here. The formula is this. I think it's a 2 in the textbook. You got to be really careful with your limits of integration. I told you what you should try. You should try graphing on the graphing screen and try multiple things for your domain, right? Don't always do 0 to something, okay? In this particular picture, I would think that it would be wise to choose between a negative angle and a positive angle. See? I don't think I'd do 0 to pi over 2 on this problem. I might do like negative pi over 2 to pi over 2. You know what I'm saying? To capture that little pedal. So it turns out it's actually negative pi over 4 to positive pi over 4. You'll find out so obvious. You guys can work